Everybody, hope you're doing well out there. Getting some sunshine before the polar vortex rolls in this weekend. We're going to wrap up our discussion of stars today, talking about nuclear fusion and black body radiation. Thank you for those of you who were there on Monday for the mandatory check-in. It's pretty painless, 15 minutes. Please keep going to those links at the time scheduled, and that way we can touch base and do attendance and give overviews for the week. And with that, we'll jump into nuclear fusion. So a couple learning objectives for you today. This is kind of a rerun of what we did last assignment, but we'll touch back on it. I can describe how stars produce heavier elements through nucleosynthesis. I can describe how stars produce energy through nuclear fusion. And I can describe how stars give off electromagnetic radiation through a process called black body radiation. So we're basically going to talk about what do stars do. And stars do two things. They produce elements and they produce energy, and that energy is eventually given off in the form of light, electromagnetic radiation. Before we jump into it, I'm just going to run us through a little story of our distant family tree, try to place us in the timeline of the history of the universe. So we've already studied the Big Bang, roughly 13.7 billion years ago. According to the scientific evidence, the universe began in what we call the Big Bang. And in the first about 500,000 years, simple atoms of the elements hydrogen and some helium formed as the universe expanded and cooled. But our solar system, including Earth and the Sun, is only about 4.5 billion years old and made up of 92 naturally occurring elements. So that might beg the question for you, as it does for me, what happened in our cosmic neighborhood of the Milky Way galaxy between the formation of the universe and the formation of our solar system? Here's a quick image, kind of a timeline of the universe. Sorry for the poor quality. But what I'm talking about is here after the Big Bang, we saw this development of atoms, mostly hydrogen. And then 9 billion years later, we see the formation of the solar system, which has a bunch of different elements, way more than just hydrogen. And so we're going to try to fill in that gap of what happened in between the Big Bang and the creation of our solar system. And between the creation of the universe and the creation of our solar system, a few things happen. A massive sized star, what I like to call our grandfather star, lived its entire life. And it might have been more than just one star. Some people say there's been as many as 2 generations of stars that came before our sun. But it lived its entire life, and through its lifespan, it produced the elements that make up our planet and us in its fiery core inside that star. It exploded in a supernova. I'll talk about how we know that in just a bit. And then from the nebula left by that explosion, from this cloud of dust and gas left by the explosion of that star, Earth, the Sun, and all other planets started to pull together through gravity into the solar system we have now. So looking at this life cycle of a star chart over here that we've talked about before in previous assignments, this is kind of how it would happen. In the neighborhood of our region of the Milky Way, there's a stellar nebula, a cloud of hydrogen that condensed under gravity into a massive star. That star lived its life. It's a very large star, so it had a shorter lifespan than our sun does. But as it lived its life, it produced elements. It eventually exploded in a supernova, producing even more heavier elements. And then left behind was a planetary nebula. And that planetary nebula is what our sun and our planet, Earth, and all the other planets of the solar system were able to form out of. So that leads us to a couple of quotes that are my favorites. They're both Carl Sagan quotes, and they're kind of two phrasings of the same concept. The first is, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. And the second quote is, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. We'll double back on this concept at the end of this, but I think it's a pretty cool idea to know that all of the elements inside my body were produced in the life and explosion, the death of stars that came billions of years before our solar system. So, what do stars do? The first thing is nucleosynthesis, which you've already read about a little bit. Due to the extreme heat and pressure of stars, small elements, mainly hydrogen, are fused together. And when you think of fusion, with that vocab word, I'd think of sticking together. So here's a real simple diagram where you can see smaller pieces are stuck together inside of a star to form eventually a bigger piece. In this case, we have hydrogens coming together, adding more pieces, more neutrons, and eventually making a helium atom. This fusing of small elements creates larger elements in a process that we call nucleosynthesis. Nucleo refers to the nucleus of an atom, and synthesis means to create. So nucleosynthesis literally means the creation of atoms. And I'm actually going to double back to that real quick. Here is a familiar image. It's the periodic table. But what this particular periodic table does is it displays how those different elements are produced. And just to emphasize a couple points, hydrogen and helium at the top here, the lightest elements, were produced in the Big Bang. But larger elements, the vast majority of the periodic table, were produced through stellar processes, either inside large stars, small stars, the cosmic rays that stars give off like solar wind, or in supernova, the explosion of stars. A couple more comments on nucleosynthesis. The nucleosynthesis of different elements happens at different layers in the star, kind of like an onion. Heavier elements require more heat and pressure to fuse, and therefore they happen deeper inside the star. And nucleosynthesis in a star generally stops at iron, with heavier elements beyond that, like gold or silver, being produced in supernova explosions of stars. So here on planet Earth, we have iron, we have carbon, we have gold and silver, and so we know that there must have been stars out there that lived their lives and blew up to give us those elements that we can then produce apple pies or jewelry out of. And here again, we see that process of smaller atomic nuclei, smaller atoms, fusing together, sticking together to form heavier and heavier elements. Which brings us to the next piece, what stars do, nuclear fusion. And nucleosynthesis and nuclear fusion mean the exact same thing. They describe the same process, the fusing together of small elements to produce larger elements. So here's just another simple model of two isotopes, two types of hydrogen that come together in the process called fusion to produce a helium nucleus. But the other thing is, in the process of nuclear fusion, energy in the form of light and heat is also produced. So in this particular diagram, we see that arrow representing energy as a product of this reaction. Scientists like to use the term nucleosynthesis when talking about atoms being created, and nuclear fusion when talking about energy. So you might wonder, if they mean the same thing, why do we have two different words for the same processes or two different phrases? One is more in the context of producing that helium atom or producing that carbon atom, producing heavier elements, and the other is in the context of producing energy. Nuclear fusion is the same process that happens in a hydrogen bomb, which is mankind's most powerful nuclear weapons. And so one way to think about a star like our sun is just this big nuclear explosion in the sky. So that brings us to our extension on nuclear fusion. This piece is a little complicated. We're going to talk qualitatively about an equation, E equals mc squared, and this is a part of the PD extension of the assignment. Nuclear fusion can be explained using Einstein's famous equation E equals mc squared, where E stands for energy, m is for mass, and c squared is the speed of light squared, which is a very large number. So just in that equation, we can see that we're relating energy to mass through this concept of light. It's a very elementary explanation of that equation. The equation relates how mass is really a tightly locked up form of energy, and that energy is released when a small amount of mass is destroyed. And so what we mean by this is these 4 hydrogen atoms in the beginning of this nuclear fusion pathway, if you were to add them all up, would weigh less than this, or excuse me, would weigh more than this one helium atom produced at the end. You kind of flow from top to bottom through this. So the 4 pieces going in are heavier than the 1 piece coming out. And that means that some amount of mass must have been destroyed, and that mass was converted into energy. It's a confusing and not an intuitive concept at all. It's kind of like if you had 4 Legos and you weighed them individually, their mass would be more than if you put them together into a sculpture and then weighed them after. The total weight of the products of a nuclear fusion reaction is less than the total weight of the reactants. What goes in weighs more than what comes out. And that lost mass is made up as energy. And this brings us to our last piece about what stars do, which is black body radiation. Electromagnetic radiation, light, as we've been calling it since way back when we were still in the classroom, is naturally created when charged particles, such as electrons and protons, move around. We saw this with the emission spectra being produced as electrons move between energy levels on the outside of atoms. But light is also produced by all objects because of their temperature, which is a measure of how fast atoms are moving around inside an object. So something like even my desk right here, it collectively is stationary, the desk is not moving, but the individual atoms inside this desk are wiggling back and forth because of the heat that they possess. As those atoms move, so do their protons, a charged particle, and the hotter the object is, the faster the protons move. And the faster the protons move, the more energetic the light produced. And we call that concept black body radiation. It's the explanation for why I, made of atoms, and those atoms are in motion because I have a temperature, why I give off infrared light. Now I am relatively cold compared to a hot piece of metal or a star. And so the light that I give off is only in that less energetic part of the electromagnetic spectrum, the infrared zone, but I am giving off infrared light. And if you had an infrared camera, you could see that. And you could also see that my skin would be warmer than my hair and therefore giving off more infrared electromagnetic radiation. If you've ever had a blowtorch and a piece of metal and been able to heat that metal up to the point where it's now red hot, it is glowing in the visible spectrum, starting to give off actual light that I can see with my eyes because its temperature has passed that certain point to push the radiation given off into the visible spectrum and no longer just in the infrared spectrum. And so now let's take that concept to stars. I'm going to turn the webcam off for a second. And stars emit light based on their temperature. The hotter the star, the more their radiation is increased. and push towards the UV side of the electromagnetic spectrum. And so this graph down here, it's a little complicated to understand, but along the x-axis, we have the electromagnetic spectrum. Over here on the right, you'll notice is infrared, into visible, and into ultraviolet. If it kept going, we'd see that there's X-rays and then gamma rays. So it's important to keep in mind that the left side of this is the high energy side of the spectrum. The right side is the low energy. And along the y-axis, we have the intensity. You could think of that as like the brightness of those different types of light. And then in the actual graphed space, we have our curves. And those curves are for different temperature objects. So this 3000 Kelvin, which is a unit of temperature used in science, this coldest object is radiating only slightly into the visible spectrum. That curve only just barely enters the red and the orange part of the spectrum. It's primarily in the infrared part. And so that would be like the red hot piece of iron. I'm starting to see it glow, but it's glowing red and not white or blue. As objects get hotter, that curve is starting to push into that higher end of the electromagnetic spectrum. It's starting to move more towards the ultraviolet side, and it's starting to grow. It's just becoming brighter in general. And so what we see here is an object like 5000 degrees Kelvin would be similar to our sun, where now it's giving off all colors of light, and that equates to it being a kind of yellowish white color. And it's also giving off a pretty significant amount in the ultraviolet section, as well as, of course, that amount in the infrared section. Some of the hottest stars out there are glowing blue because their peak has now been moved all the way towards the energetic side of the visible spectrum, which is, of course, the blue-purple side. This explains why smaller, cooler stars are red to yellow, like our sun, and the very large, very hot stars are white to blue. It's again about where that peak is falling along the graph. The radiation curve of our sun, which I said was around this 5000 K mark, is giving off electromagnetic radiation in infrared, visible, and ultraviolet. So just to wrap it up real quick, I kind of talked a lot about what do stars do. They produce elements and energy through a process called nuclear fusion or nucleosynthesis. And then that energy is radiated as light through a process called black body radiation. But we haven't talked yet about what do we owe stars, other than that quote in the beginning that we are made of star stuff. So we just learned that stars primarily do two things. They create heavier elements that can gather into solid planets, living organisms, my desk in front of me, an apple pie. And they produce and give off energy in the form of light. That's a typo. That's supposed to say plants, not planets. But plants can use to support a food chain in an ecosystem. And so without these two things, life, including you and me, would not be able to exist. So we literally owe our life to stars. And that's not just the sun, but it's also the stars that came before us, those grandfather stars that produce those heavier elements that could make up our ecosystems. And so at the next assignment, we're going to finally leave outer space behind us, and we're going to pick back up on planet Earth as that sunlight, having traveled about 8 minutes from the sun, strikes our planet, which drives the climates, ecosystems, and societies here on Earth. And with that, I'll post a new assignment and check it out. Shouldn't take too long. If you have any questions, comments, concerns, please send them my way, and I will see you all on Monday. Be well.